I want to stay on this calculus topic where we just talk about series and whether the power series that I have here converge or diverge. Let's jump right into it. Let's take a look. All right, so if you look at this, what we've got this issue of an alternating sign here, the -1 to the n plus 1. So what I want you to be able to see here is another way of writing this. If we ignore this alternating piece, which is what you have to do when you're examining an alternating series, you take the absolute value of this, which would mean to ignore this -1 to the n plus 1. If you do that from n is equal to 1 to infinity, what you end up with is n raised to the half, same thing as a radical n, over n raised to the 1/3. All right, any kind of hopefully you can see that. I don't think you can see that. All right, let's work on that a little bit. So n to the 1/3 power. N to the 1/3 power. So that's the same thing. You're summing n is equal to 1 to infinity of n to the 3/6 divided by n to the 2/6. So we get from n is equal to 1 to infinity of n to the 1/3 power, n to the 1/6 power, n to the 1/6 power. So that is, you're summing n is equal to 1 to infinity of the 6th root of n. And if you put infinity in there, you'll discover that the limit of this is infinity. The limit of that is infinity, which would mean that this diverges. This diverges based on the nth term divergence test. The limit of this must be 0 for it to have a chance to All right, so converge. Now what we have is another series. This is another series, alternating series. You got this numerator changing the sign. As n changes, this is going to flip-flop the sign. So the test that we learn for an alternating series is to apply the limit as n goes to infinity of this series absent what's causing the series to alternate. So you take the absolute value. If you analyze that limit as n goes to infinity, ignoring this numerator temporarily, 1 over n times the natural log n, you apply this limit, it equals 0. And that is a requirement for the alternating series to converge. And then you have to ensure that as n gets larger and larger, this series gets smaller. That's also a requirement. And if you notice that the denominator would get increasingly larger, which would force the overall fraction to get smaller as n increase. So that's the second criterion which would be met. So therefore you can say that this overall series, alternating series, converges based on the rules of the alternating series. All right, so if you have any questions on that, I want you to call in. First problem diverges. This next series converges. Let's look at this problem right here. All right, you got this 3 to the n, 2 to the n. I told my students, when you see a lot of n's like that, that's a giveaway that you might want to consider using that ratio test. And again, this video, or excuse me, these problems that we're doing, I'm assuming that you've seen these tests already, and I'm just reminding you of the tests that you've already talked about. Maybe down the road what we'll do is actually spend time going through these tests in more detail. All right, so let's keep going. Here we go. All right, so for this particular test, this ratio test, again, you're taking the absolute value of this, so that would get rid of what's causing this series to change. So you apply the limit as n goes to infinity of a sub n plus 1, the absolute value again, over a sub n, all right, and you apply that. And if this limit is actually less than 0, or excuse me, less than 1, I apologize, that is an indicator that this series converges. All right, so let's do that. All right, so what we end up with is a limit as n goes to infinity of 3 to the n plus 1 over n plus 1 times 2 to the n plus 1, all right? And that's going to be divided by this same series without substituting in the n plus 1. So you get 3 to the n over n times 2 to the n. All right, so let's evaluate that limit as n approaches infinity. All right, so the limit as n approaches infinity, this numerator would be 3 to the 1 is 3, times 3 to the n, and that would be divided by n plus 1 times this 2 times 2 to the n. All right, 2 times 2 to the n. This can expand into 2 times 2 to the n. And let's multiply that by, this would be in the numerator, dividing fractions means multiplying by the reciprocal. So this would be n times 2 to the n. Let's separate this so you don't confuse the two. N times 2 to the n over 3 to the n. All right? All right, so now you have cancellation. That cancels with that. This 2 to the n cancels here. And what we end up with is the limit as n approaches infinity. Limit as n approaches infinity of, you end up with 3. Actually, let's say n, okay, n, this n over n plus 1. And outside the constant, you would have 3 halves. So we have 3 halves, this 3 halves times the limit of n over n plus 1. And don't forget that we're applying, the limit as n approaches infinity. So as n approaches infinity, this limit is 1. All right, so this is 1. So you end up with 3 halves times 1. And what I told you before up here is I said as you apply the limit as n approaches infinity of a to the n plus 1 over n, if the result is less than 1, well, that means that the series that you have converges. But this is 3 halves, which is greater than 1, which would tell you that this overall series would diverge. All right? So if you have questions on that, give me a call. If you have questions on that, call in. All right? So what I want to do is I want to look at another problem. We're going to do problem after problem after problem unless you call in. Number 312-738-1060. I've got plenty of problems. The show works best if you call in, but what I'm going to do is I'm going to put these videos on my YouTube channel, Dominate Math. So if you want to practice not just calculus problems, but algebra, trigonometry, pre-calculus, all kinds of problems are on dominatemath.com. You visit that to study for your test. Let's take a look. We got more problems. All right, so one of the things I told you over here was if you see a lot of n's, 3 to the n, 2 raised to the n, that's a giveaway that you're going to use this ratio test that I use here. Also, another giveaway that you're going to use this ratio test is that you see that factorial. You see a factorial there. That's another giveaway. We're going to be practicing this ratio test. All right, so let's do that here. All right, so again, what we have is we have the limit as n goes to infinity of the absolute value of a to the n plus 1 over a to the n. All right, and again, if this is less than 1, your series is going to converge. All right, if it's greater than 1, all right, that's a giveaway that your series is going to diverge, as in the last problem that we did. So here we go. So we have 2 to the n, 2 to the n plus 1, all right, and that is factorial over n plus 1 to the 5th. That is over this same series, 2 to the 2n factorial over n to the 5th. All right? The only thing I did was substitute in n plus 1. I put in n plus 1 here, n plus 1 there. That's my numerator. and then I kept the series the same in the denominator. All right, so now what we're going to do is apply the limit as n goes to infinity. All right, so what I'd like you to do here is the limit as n approaches infinity of, this is 2n plus 2. This is 2n plus 2 if you distribute that in. So that's 2n plus 2 times 2n plus 1. I subtracted 1. And then times 2n minus 1 and so forth. But instead of saying all that, you can just say 2n factorial. All right, so 2n plus 2 times 2n plus 1 times 2n factorial. That's all over n plus 1. You'll see why I expanded that in a minute. N plus 1 to the 5th. All right, and let's multiply by the reciprocal. Times. All right. Let's get this out of the way so there's no confusion. All right, so times this numerator, n to the 5th, multiplied by the reciprocal, over 2n factorial. Over 2n factorial. All right, so now what you have is this would cancel here. That's why I expanded that out. All right, so now what you have is you have the limit as n goes to infinity of n to the 5th over n plus 1 to the 5th, and let's multiply that by the limit, as you still have another part of this limit that we had to evaluate. All right, so we've handled this part of our series already. So we have the limit as n goes to infinity of the rest of this power series. We get 2n plus 2 times 2n plus 1. All right, so anytime you have a product, anytime you take the limit of a product, this times this, you can break it off into the product of two different limits. That is a property for limits. All right, so now what you have is if you were to apply this a limit, you'd eventually, if you expanded this out, you'd have n to the 5th over n to the 5th, and this would be 1. The limit of that would be 1. Times the limit as n goes to infinity of this product of two binomials. Hopefully you can see if you put infinity in here and here, you'd get an incredibly large number. You'd get infinity. So you get 1 times infinity. We only have 1 minute left. We got to hurry. So you'd have 1 times infinity, which would be infinity. And we told you before that if the limit as n goes to infinity of a to the n plus 1 over a to the n, if that's less than 1, your series converges. But if it's greater than 1, your series diverges. Clearly, infinity is greater than 1. Infinity is greater than 1. So the answer to this is the series diverges. So that's all we have time for.